Just so we can see that. All right. Okay, so there we go. Okay, so welcome to last class. We talked about last class, we moved away from descriptive statistics, we moved into inferential, drawing inferences. Last class, we talked about our numerical data. This class, we're going to talk about categorical, and the tests that go along with categorical data. So my goals for this evening, we're going to just do a really quick review to make sure we're still on the same page regarding descriptive versus inferential and some of the other key terms that we went over. We'll learn how to identify when differences between categorical groups are significant or not. There are a couple of tests that you can use for that. You'll learn how to use Excel. Specifically for tonight will be chi-square and an Anova test. So those are the two that you'll learn this evening, and we'll use real world data again. But really quickly, and I'll fly through this because we've reviewed this a couple times now, just in terms of population versus sample, we're typically mostly looking at sample data. And what the beauty of the central limit theorem is that we can take sample data, we can use inferential statistics, and we can generalize to that greater population without actually having the population data. When we're working with the data set, the first step is to just calculate your descriptive statistics. Just to summarize the data, it's kind of like the getting to know you phase. So anytime that you're writing a report, you report out these descriptive statistics so that the reader can get an understanding of the bulk of the data. It's a way of summarizing it. So the descriptive statistics, we learned about how to run that from the data analysis tool pack. Those are some of them, and you pick and choose which ones make the most sense to share. So we talked about why you would pick mean versus median, for instance. So then after that, you would look at and identify at least if there are any outliers in your data. And what's the test that we use for that? IQR. That's right, you use the IQR, good. And so the IQR, you identify Tukey's fences, so those upper bound and lower bound, and any outliers are what fall outside that upper bound and or lower bound. And so then your choice there is to remove any errors. So if there are outliers that are erroneous for whatever reason, you can take them out of your data set without a worry and to continue on. If you have any outliers that you think are legitimate, then you have to stop there. You can't run any of these other inferential statistics because they are no longer effective once you have outliers. So that's where you stop and you share, well, okay, we have these outliers and these are significant. And this is probably where we need to begin our work. There are these people or these groups that are so far outside of the norm. But if you are able to remove the erroneous data, that's where you can go a step further and really begin to talk about what the average is and what's not average anymore. So we looked at a couple.
Remind me how you know. You don't know whether they're going to be, whether it's a mistake or you have to test it.
It would be, so I would just go back into the data set and look at which ones are standing out. And you might need to go back to the person who did the data collection. You might just see what the error is, that there was a decimal place put in the wrong spot. It might just require a meeting to be like, hey, here's the information that I have. Does this make sense? Or does it seem like there's something wrong here? Yeah. It really just depends on how close you are tied to the data, if you would know by looking at it or not. So once you have, the whole point of eliminating those outliers is to take your bell curve from this with the long tail on either the right or left side and get something that's a little bit more normally distributed. This isn't the best example, but a bell curve that's more distributed. And the reason is because now we can start to make generalizations about where our data is falling in relation to the mean. And that comes from the central limit theorem. So again, descriptive statistics, things like the mean, median, mode, the IQR. Pearson's correlation falls as a descriptive statistic. But then also, if you have that bell curve, you can also do inferential statistics, and that's what we started talking about last class. So we looked at the t-test, and we looked at Pearson's correlation in terms of generalizing to the greater population. So it's the one that's flexible between the two. And as you can see here, we're going to talk about Anova, the second one on the list. Manova is, I'll share with you what it is, but it's very similar to Anova. It's just a little bit more powerful. And we looked at chi-square, and regressions, we'll talk about again what that is and what it can do, but we won't go over how to run it within Excel. Quite frankly, I would say once you're moving into inferential statistics, in my opinion, Excel is not the best way to do it. It becomes really laborious. I would use something more like R, Python, SPSS, SAS, whatever it is that is your tool of preference. But you'll see today, it becomes more challenging to run these tests in Excel, which is why we're not going to go into depth. It's just good to know that you can do it if you need to. Okay, so then we also talked about the difference between numeric and categorical. Last class was numeric, this one was categorical. What's the difference? Can anybody summarize?
Numerical, you can quantify it, it's literally numbers, whereas categorical are descriptive. They're not numeric. It could be a zip code, but those numbers don't mean anything.
Yeah, great.
Numeric means to continuous, essentially.
Yes. Yeah. It's numeric is the umbrella, and then there's discrete numeric numbers and continuous numeric numbers. The tests that we're looking at are continuous. But yes, it falls under that umbrella.
It's
Numeric. It's the
numeric. We have two categories. You said we have continuous and what?
discrete. Yeah.
Can you spell it?
D-I-S-C-R-E-T-E. Discrete. The difference between those two, continuous is every number, even if it's a fraction of a number, has significance, whereas discrete might just be whole numbers. For instance, it's 1, 2, 3, 4, 5, but a half of a number doesn't make sense. So for instance, if you were doing a participant satisfaction survey, the number of participants who gave you feedback would be a discrete number because you're not going to have 3.5 people who responded. You would only have 3 or 4. Does that make sense? Okay. So the other big thing, and where people often get tripped up when deciding whether it's numeric or categorical, is my test is always, would it make sense to do an average of the numbers? Numeric, yes. Categorical, no. Where people will get caught up is if you were to code any of these examples of categorical data. So for instance, when you're running SPSS, for instance, gender, you can't have inputted as M or F and run a test off of it. What winds up needing to be done on the back end is a coding. So male might become 1 and female 2 and other 3. So people can get confused and think that they're dealing with numeric data for that reason. And so again, it's just always the question of would it make sense to do an average? Would it make sense to do an average of 1, 2, and 3 as the gender code? No, because I don't know what 1.5 would be. It's nothing. So there's that. And then again, we looked at these continuous, the numeric variables, and 2 ways of comparing them. We looked at the t-test, and that's how we want to look at 2 groups, and we want to see if their means are different from each other, and if there's a statistically significant difference. Correlation, it looks at the degree of a relationship. So that's not necessarily, you can't say which one is causing the other. If you were to set up a controlled environment, and you could say, okay, well, it's an example, like height and weight is a good example of a correlation. Yes, one usually goes up when the other one goes up, but I can't say whether, well, actually you can say whether one hits the other. Your weight is not going to cause your height to go up. It's the height that often causes the weight to go up. So again, if it's a controlled environment like that, you can logically sometimes draw that conclusion of what's causing what, but it's not always the case for correlation. Sometimes the only conclusion that you can make is these two things are linked, and I need more information as to why. So today, the question is, how do I build a case of a causal relationship with categorical data? And of course, I have other things I want to teach you before then. So let's talk about some vocab for categorical data that's important to know. The first one is the difference between independent and dependent variable. And we talked about this a little bit last class. So just to kind of review, what is the difference? When we're talking about cause and effect relationship, one of them is the cause and one of them is the effect. Who knows which one's which?
Dependent is the effect.
Yeah. And it's literally because it is dependent on whatever the input is that you're putting in there. So the independent variable, it's the quantity that's being manipulated. That's what you're changing. I am affecting it. And then the dependent variable is what's being changed because of how the independent variable is being manipulated. So some examples: time spent studying has an effect on the final exam score. And as you can see, they're often annotated in parentheses with IV and DV. IV independent, DV dependent. And then the final note at the bottom, many evaluations use independent variables and dependent variables to provide evidence of a program or an intervention's effect. Once you have identified what your independent variables are and your dependent variables, you're able to, like I said, run this test and be able to say, okay, one thing caused the other. So this grid is going to carry us through class, and we'll fill this in as we go. But this is just a way of organizing what we've done already and what we're going to continue to do. So the research question, when it comes to correlation, it's a little bit different. The research question here is, to what degree are two groups related? Again, we might be able to talk about cause and effect, but sometimes we're just not able to. But we can say that they're connected to each other, they're related to each other. So the goal is to determine the relationship between the two groups. When it comes to the independent variable, you can use either continuous, numerical, or categorical. And then there's this descriptor down there, the one category with two levels. I'll explain what that means in just a moment. But at least know, for now, the independent variable can be continuous or it can be categorical. But the dependent variable has to be continuous. It cannot be categorical. So then an example is a relationship between residential noise complaints and business complaints. And then the name of the test is the correlation. So similarly, we're talking about building a causal relationship. So are there differences between the two groups, and are they statistically significant? We looked at the t-test. And for that one, the independent variable needs to be categorical and the dependent variable continuous. So an example of that, does weekday or weekend affect the number of complaints that we have? So, first of all, any questions about that? Again, I'm going to fill this in. Basically, at the end, we'll have a chart that you can use anytime that you say, okay, I have this independent, I've identified what my independent variable is, I've identified what my dependent variable is. I know I want to run a test to find out if there's a cause-effect relationship, but I don't know which test to choose. This is a chart that you'll be able to use to pick that, as long as you can tell the difference between continuous and categorical. All right, so we'll keep going.
Hello?
Yeah.
I have just to understand the third column.
Okay.
Where they said categorical, one category was only two levels. What's missing is two levels?
I'm going to answer that right now. Thank you for that question. So when it comes to a data set, there are some things that are important to understand. They're organized into columns and rows, right? A really good data set, columns and rows. So that's A through whatever and 1 through whatever. Each column represents a variable. So this is any good data set. So each column, for instance, with our noise complaints, we have the date that it was open, the date it was closed, all of those things are variables. And then each row represents an instance. So they're each a unique instance. The values in each of the cells are called the data. So each of those points is a data point. And the variables can be continuous or categorical. So, oh, another important point, the categorical variables groups are called levels, bless you. So what do I mean by that? Let's look at our data set. The variables run across the top, right? Again, the unique key, created date, closed date. Each row is an instance. All of this is our data. The continuous variable, so date is an example of a continuous variable. An example of a categorical variable are the descriptors. And then each of the levels are groups. So I pulled out a filter here. And these are the unique descriptors that are in the data set. There are 4 of them. And so what we would say is that there are 4 levels to that categorical data. Does that make sense? So then I would go back to this chart, and that's where this becomes important. If you're using categorical, you can have a category, that's fine, but it can only have 2 levels. So if we were doing gender, for instance, you could only do male, female. You couldn't have any other option. There are other tests if you want to have more than 1 level or more than 2 levels. Okay, so there's that. So then the question is, how do I compare 2 categorical variables? And the first test we'll look at is the chi-square. So we're going back to the grid. We want to build a causal relationship. We have categorical data, that's our independent variable. You'll take 1 category, and this one can have 2 or more, so as many as you want, levels. And then similarly, your dependent variable is set up the same way. So you're looking at just 1 category, 1 variable, but it can have more than 1 level, so as many as you'd like. So it becomes a pretty powerful test in that regard. An example, does Burrow affect the complaint descriptors? So Burrow, categorical, and there's definitely more than 2. And then complaint descriptors, and we just saw that there are 4 or more. So chi-square, it identifies if there's a relationship between 2 categorical variables. It tests if there's a difference between the expected frequencies and the observed frequencies. So what we'll wind up doing is we'll be creating a table of what the actual frequencies are of the types of complaints per borough or by borough. And then we'll calculate what we would expect to see. And that'll be straight math, which Excel will be great and very helpful to do. And then the chi-square is going to compare those 2 tables to see if there's a significant difference between the 2. And if there is, then we can conclude that there is a significant, that borough does affect the complaint descriptors. So as evaluators, it's useful when we want to, ahead of time, before a study, an evaluation, we want to identify if 2 of the groups are similar to each other. After an evaluation, or if we're doing a summative evaluation, it's if we want to determine if 2 groups are significantly different after we implement a program or after we implement an intervention. Very similar to any of the other tests that we've talked about so far. So in Excel, there are a few different types of chi-square tests. We'll be using the one for goodness of fit. I would say that that's probably the most common one that people use. Its formula is pretty easy. It's equals chi-square, abbreviated, dot test. And like I said, there's some pre-work that needs to be done creating those tables. Once you have the tables, it's very easy. So what you'll need your 2 sets of data, and they'll have to be, each of them will have to have the categorical information. I guess you could have it within 1, but you need 2 categorical variables. You'll need your null hypothesis, and that was just the same as last class. Your null hypothesis is that there's no difference between the 2, what you expect and what is actually happening. You'll need your desired alpha value. This is, again, the same as it's always been. Most common is 0.05. Another next most common is 0.01. So let's try it. And actually, before I click on this, I'm just going to walk you through how we'll do it, and then we'll go back and forth. So what we'll do is we'll start with our class data. We'll create a pivot table. Is everybody familiar with pivot tables? I think, okay. It's pretty straightforward if you're not. So we'll create a pivot table. What we're going to do is take our first independent variable. So for us, it'll be borough. The question that we're asking is, I think, does borough impact, what was our question?
Does borough affect?
Does the number of children a person has affect the borough in which a person lives? So we'll take the borough and we will place it as the columns so that we can get them running across the top. And then we'll create tables. So we want the count of number of children in the rows and the count filled in. So here's the number of children, and here's how many people had 0 children in each of the boroughs and 2 children in each of the boroughs. So once we do that, we're going to copy and paste it. So we're going to copy and paste it twice. We'll create a table that we're going to title observed and a table that we're going to title expected. The observed data is just going to be exactly what we pulled from the pivot table. When it comes to expected, we're going to need to do a little bit of math. So the steps will be for expected, we're going to create a formula to tabulate what the grand total will be. So we'll create that. The next step will be to calculate the data in here. And the way that we'll do that is take the observed column subtotal, we'll multiply it by the observed rows subtotal, and we'll divide it by the observed grand total. That's always where I lose people. But it looks like this. And again, you can go back and forth, and we will go back and forth from the slide to the data set in order to do that. Once we've got it created, what you'll find, the test to make sure that you did your math correctly, is that your subtotals and your grand total will be the same in the end. That's why we create this formula down here to add up what's in here. It's our test to make sure that we did the math correctly. And then we run the chi-square test. So I'm going to go back here. Let's look at what slide it is. So we're on slide 37. So if you're not there, go ahead and get there. Click on the link, and then let's download a copy. It was slide 37. And if anybody's sitting there thinking, okay, well, Liz just said that the dependent variable and the independent variable need to be categorical, but number of children is numerical. You're right. We're doing this just to illustrate with a small data set how to do it, and then we'll go and do it with 2 categorical data. This, we only had 1 categorical data, and that was borough. All right, does everybody have the data set? So the first step is just going to be to insert the pivot table. So we'll come up to the Insert tab. You'll click on Table, and you'll click on that first option, which is Pivot Table. You'll get a pop-up, and you can just click OK. It'll open a whole new tab for you. Does anybody need to see that again? Are we good?
Still saving my
Okay. I'll delete and get started over. Excuse me. Let me know when you're ready.
Yes.
Okay. So just click in any single cell. You don't need to highlight the data. You'll go to the Insert tab. That first option is Tables. And you'll click Pivot Table. And then once you do, just click OK. And you've got your pivot table. So then flipping back to the slides, the instructions are to place your independent variable in the rows and your dependent variable on the columns. So our question was, does borough impact the number of children that somebody has? So we're going to look at borough. Let's look at NYU borough, because that's you. And we'll put that in columns. So it fills it in automatically for us. And then we're going to take the number of children for NYU and put it into the rows. So that then fills in, we had 1 through 3 children. And then you'll take number of children, click on it again, and this time drag it down into the values. And what that's going to do, let me just expand this. What that's going to do is fill in our table for us. So you can see that there are 3 people who live in Manhattan who have 0 children. There's 1 person in the Bronx who has 1 child, 1 person in Manhattan who has 1 child, and so on. You want to see that again?
Yes.
Yeah.
So it's borough and children, right?
Yep. And it's the, it is the independent, it's the independent variable that goes in the rows and the dependent that goes in the columns. So we want to know, is that how I did it? Yeah, I guess it would be the opposite, wouldn't it? Yeah. So really this is asking, let's reverse it. So our independent variable, what we're impacting is the borough, right? So let's put that in the rows. I apologize. And then the number of children, we'll put that in the columns. And then again, to fill it in, let's just take number of children again, and we'll place that this time in the values, and that'll fill in the count.
Children in NYU.
Yes. Yep. So we've got borough in rows, number of children in columns, and number of children in values. In the end, it's not too big of a difference. Does everybody's table look like this? Yeah.
What's in values? My eyesight is very bad.
It's the number of children for NYU.
I got grand total of 10. That's what I have to.
What? Did you just download it from the website?
Yes.
Why does that keep happening? All right, let's look at, what's that?
Mine says sum of the values.
Maybe that'll change it. So we do want count, and that is a way. Excel tries to intuit what you're looking for. Sometimes it'll add it together. So if yours says sum here, you'll want to change it. You can do that by clicking that arrow on the far right. Select that bottom option, value field setting. And then change it to count. Yep. And click OK. Does everybody have 9 now?
Yeah.
Oh, good. Thank you for catching that. Okay. Yeah. Good. Okay. So the next step was to copy and paste this twice. So one tricky thing about Excel is that you can hit Control-C to copy it. But if you want to paste it, you do not want to just hit Control-V. You want to special paste just the values. So you can right click and just select this paste of numbers 1, 2, 3. Do you see that? You just want the values. You don't want any of the formatting. You don't want it to be another pivot table. You just want those numbers. So you can do that. And then a couple rows down, paste it again. So for me, I just want to do some aesthetic things. So for instance, it's driving me crazy that B is so big, but C, D, and E are not. So I'm just going to make them all the same size. I wonder if it's going to let me hide F, but I would like to. Yes. All right, so I'm going to hide F. I don't want my blanks in there. I'm going to hide my blanks. Actually, yeah.
Sorry, Liz, are you currently on an Excel or are you working on Excel?
Oh, no, you can't see it, can you?
Yeah, I can't see it. Yeah.
Sorry about that. Let's see, how do I change? Let me just share my screen. How's
okay,
that?
yeah, now I see it.
Okay.
Thanks.
You're welcome. Okay, so let's delete our blank entries since that is not needed in our table. The other thing I want to do is just make it look like a table. So I'm just going to add borders. I'm going to make the column headers and the rows a different color just to make it stand out a little bit. This is just aesthetic stuff to make it easier to look at. So once you've done that, we need to title these just so we don't confuse the two tables. Let's call the first one the observed. And then the next one we'll call the expected. Okay. How's everybody doing here? Ready to keep going? Okay, so in our expected table, let's just delete all of the data. So anything that's in the white section. And like I said, we're going to do a formula that's going to fill in this data from 0 to 3 and from Bronx to Queens. But to make sure that we're doing our formulas correctly, it's helpful to have automatic formula here that's just going to sum up what the data is so we can check it and compare it to this information here. And the way that we'll do that is just create the sums. So it's equals sum. And we just want to sum up everything that's in the column above it. Does that make sense? It's just the subtotal for that column. And you can click and drag that over because it'll transfer the formula over a column. And then similarly for the rows, to get your subtotal of your rows, you'll do sum again. And this time you're just going to highlight the data in the rows. And you can click and drag that as well. In the end, for this one down here, it doesn't really matter whether you're summing the columns or you're summing the rows. So I always check when I click and drag a formula just to make sure it did it correctly and I look like I'm good. Does anybody want to see any of that again?
Yes.
Great, I can do that. So what we're doing is creating this number, basically. And this number, this subtotal, is adding up anything above it in the column. So we're just going to do equals sum is the formula. And we're just going to highlight all of the cells above it. So anytime we put numbers into those cells moving forward, this total will change. And I can show you. If I were to put a 1 here, it automatically changes to 1. If I were to put a 5 here, we get 6. It's just a running total for you. So I did that. to fill in the rest of the columns, I can just take this green square down in the bottom right-hand corner, and I'll just click on it and drag over. And what that does is just transfers the formula over to every cell that you highlighted or you dragged over. That's good, or we want to see that
I
again?
didn't get that.
The clicking and dragging part? You got this?
No.
So for this, you're going to do equals sum.
It's too dark. Yeah.
Good.
Some.
And then you highlight all of the cells that you want it to add up.
Yeah.
Good. And then just hit enter. And again, if you can retype it in each of these cells, or you can just hover over this green square in the bottom right-hand corner and click and drag. And then you need to do the same thing for your rows. So I'm going to go to the Bronx row, and I'm going to type in equals sum again. But this time I'm going to highlight all of the values in that row. And then you hit enter. And then same thing, you can either retype it each time, or you could hover over that green square and you could just drag it down. Good. So here comes the formula. Let's just look at it really quickly before we do it. Make this larger. So, oh, we did that already. We deleted the value.
Yes, you can.
Yeah. Let me present it. How's that?
Thank you.
Okay, so we have our formulas down here. The next thing is we need to fill in the expected values. If all things were equal, if the burrow did not impact the number of children that somebody has, this is how many children we would expect a person to have. And it's not going to be whole numbers, which is another challenge. That's why it's not discrete numbers that you use. It should be continuous. But again, this is just an example. This is not something that you should ever run. So in order to calculate the data in there, we're looking at the observed column subtotal times the observed row subtotal, and we divide it by the observed grand total. So we're looking at number of children two within Queens. That's where we're doing the calculation. And we're pulling from the observed table up here. So we're taking this number, the observed total, we're multiplying it by the columns observed total, we're multiplying it by the rows subtotal, and then we're dividing it by the grand total. Make sense? We'll do it. So let's flip back to our data set. Let's just start in the very first cell. So in Bronx with 0 children, all our formulas begin with an equal sign. And we want to take the observed column total. So for me, that's in B19, but it's the grand total for 0 children. And we're going to multiply it by the grand total for Bronx. So that's 1. And then we're going to divide by the grand total. Want to see that again? Well, first, let's see what the answer is. So it's a third. So if all things were equal, the number of people in the Bronx with 0 children, there would be a third of a person in the Bronx with 0 children. Excuse me. Do you want to see that again? Well, actually, did everybody get 0.33333? If you did, then we're just going to keep doing it until we fill in the table. So let's go over to one child in the Bronx, and let's write the formula. So it's equals. We'll do the grand total for one child times the grand total for the Bronx divided by the grand total.
I'm not understanding anything.
You don't understand why we're doing it?
Understand what we're doing.
What we're
Observed and be expected.
So these are the actual number of children that people in this room have. It's just a table of that. What we're creating is what if there was no relationship between the number of children in the borough in which somebody lives, these are the number of children that we would expect people to have. And so ultimately what we're going to do is compare these two tables to find out if there actually is a relationship between borough and number of children. What would your gut say looking at the data, the observed data? What do you all think? Do you think that there is a relationship between the two? It kind of looks like there might be, right? It looks like you would live in Manhattan if you have more than one child. To me, that's how I would interpret that. Do you see that? Actually, maybe not.
I'm a little confused, like, to calculate the data point for Bronx, the expected value, why are we using the grand total? You know, the 3, B19.
Oh, for over here?
Yeah.
Why are we using the grand total?
So I see we're doing the probability of 1 by 9. Why are we using B19 there? What does that have to do with the Bronx?
Well, it needs to be both the Bronx and 0 children. So we're trying to figure out if all things are equal, how many children would how many people would have 0 children in the Bronx? So you need to be able to compare both of those factors with each other. And then really we're normalizing all of it by the grand total.
So you're saying those 3, like grand in the first table, the 3 grand, the second column could be, I mean, you would be using the same for each of those other rows as well. Yep,
exactly. A more basic way of doing this is to just put the same number across the whole table. It's not as precise to get the answers, but that I think makes a lot more sense to people just starting out. So that is one way of doing it. What we're doing is just the more precise way of estimating. Any other questions? This is something where, you know how we looked at the formula for correlation versus what it looks like in Excel, right? Like how you would do it by hand versus how you would do it in Excel. To do it by hand, you really need to understand exactly what the math is and why we're doing what we're doing with each of the variables. With Excel, it just automates it for us. This is a good example of why Excel is not, in my opinion, ideal for running something like a chi-square. And that's because you really do need to understand at least some of what the chi-square is looking at so that you can create these tables to run it. Whereas if you were running this in SPSS, you could just highlight the information and it'll create the tables for you. It'll do everything for you in a matter of 2 seconds. So that's my way of saying don't use Excel. But if you have to, at least follow these steps to get you there. because this is what a computer would do for you otherwise. A more powerful analysis tool.
Excuse me, you got 0.33 after dividing B19.
You want to look at this one?
B19 by 9.
So we would just keep going, and you can do it with me or you can do it on your own. But again, you just keep doing, you start with the equal sign, you go to the observed grand totals for that cell in both the columns, and you multiply it by the rows. And once you do that, you divide it by the total. And then what I was explaining to you is once you have the whole row filled in, my test to make sure I did my math, I wrote my formulas correctly, is comparing the grand total for the row with the one above it. And they both should be the same. So they are right now, which is good. Once I have the whole table filled in, all of these will be the same as well as down here. So just keep going with your formula writing. And I will up here.
Elizabeth, for Manhattan.
For Manhattan.
For Manhattan, you've taken. Should you not be taking the grand total 3? If you hover on it.
For which one?
Manhattan, the first.
This one?
Yeah. B19 divided by. So why is that formula different from?
So we're in Manhattan 0. That's the cell we're in, Manhattan 0. So you have to go up to Manhattan 0 here and pull the grand totals. So here's the grand total for Manhattan.
Okay, because for bronze there was no figure. That's why the formula is different.
For which one? Sorry.
For bronze, when we did, you just took B19 and then the G15.
Yeah. So this time we were in bronze 0. So we went down to the grand total and over to the grand total. I always feel like it's a big game of, or it reminds me of Battleship, or like bingo or something, but not as fun. I think that the best way of explaining the expected table and what those values even mean that we just calculated is that we normalized our data. We have found out that if all things are equal, this is how many people would have that many children. Just like we did with the complaints per person. So again, the total is 9, but this time we have what it should look like. And then the question is, okay, well, now that it's normalized, is what actually happened the same? Or is there a difference? And that's the easy part. Does everybody have their comparison table, their expected table completed? Give you another minute. Do you want to see me doing any of it? Yeah. Is there a specific cell or?
Can you show me how you did C24?
Sure, C24. So that's Bronx 1. So I went up and I looked at 1 and that's subtotal, and then I looked over at Bronx and I divided it by 9. Any other cell you want to see? Are we ready to run the test? All right. Any other cell that you want to see before I move on? Yeah.
It's for Bronx.
Mm-hmm.
Yeah, we got that.
Which one?
Yeah, the first one.
The first one?
Yeah. The top is 0.
Yeah. So if we're looking at Bronx 0, that's the cell. We're going up here and we're pulling the subtotal for 0, multiplying it by the subtotal for Bronx, and dividing it by the grand total. Okay.
You don't need to consider the number inside of the.
No, we expect it to be different. Just like we expected the number of complaints per person to be different than the actual raw number of complaints. So if we're running the chi-square, I'm just going to label it. Oops. The formula was chi-square, and it was chi-squared dot test. Like I said, there are many types, but this one's the goodness of fit. And then it just asks you for the actual range first, and then the expected range. So when you're doing this, the important thing here, and where people can make a mistake, is you don't want to include any of your subtotals or your grand total, only the raw data. So I'm going to start in Bronx 0, and I'll highlight through Queens 3. See the distinction? I don't want to include the subtotals or any of the grand totals. Once I have the raw data highlighted, I'll type a comma. That'll move me on to the second part of my formula, where it's asking for the expected range. So then I'll come here and I'll highlight only the expected raw data. So again, I'm going to start in Bronx 0, and I'll highlight through Queens 3. Okay. What I get is my p-value. So based on the alpha level of 0.05, is there a significant difference? Or I should say, does the borough have any impact on the number of children a person has? No. Any questions about that? How I was able to draw that conclusion?
Yes, could you explain?
Yeah. So the alpha level is 0.05, right? So it's higher than that. So we know there's no significant difference. So we know it's not significant. The way to interpret it is by going back to our chart. And remember, this is the independent variable, and this one's the dependent. So our independent, does the borough have an impact on the number of children? And our answer is no. Which is actually surprising. You said sometimes it does?
Oh, it's coming up as negative. It's like the same number, but negative.
Weird.
Doesn't matter.
Did you do expected first and then observed?
Oh, there's a minus sign in front of it.
Oh, that'll do it.
So these terms significantly different, statistically different, all have different meanings, or they mean the same?
Well, and that's a really good question. So if I were to look at the numbers here, they are different, right? There's a difference between what is actually taking place in terms of borough and number of children in this room versus what would be expected. So somebody who's starting out with statistics might look at that and say, oh, there's a difference. But the next question is, okay, well, is it statistically significant? Is it a real difference, or is it just a coincidence? And that's what the chi-square can help us to figure out. And so the chi-square says, yes, I see that there's a difference between the numbers, but it's not significant. It could happen randomly anywhere.
Because it's less than b value.
Yeah. Because the number is actually greater than the p-value. If it was less, then we could say, okay, there is a significant difference. It really does have an impact on the number of children. Borough does have an impact on the number of children.
Liz, if we reverse row and column, would that give us a different number?
I think it would.
Okay. And so you would mean that?
No, I don't think it would.
Oh, okay.
No, I don't think it would.
Oh, okay. So does it matter which one is the independent variable and which one is the dependent?
Which is why I do think that in the slides, the conclusion was the same.
Okay.
Yeah. We had different data than them, but it's not a huge difference. I just prescribed independent as the row headers and the dependent as the column, just to help with instructions.
Okay.
Okay. When it comes to reporting, Again, I kind of provided what somebody might say and how you might say it. And again, you can pull out the data that's there and put in your own data. But what is typically reported is the significance level, what your alpha level was, and what the conclusion is. So there's that. And then for anybody else, you can just say that a chi-square test, chi-square test is run. The results show that there's not a significant difference. Okay. Want to try it again? I can't tell if that was a yes or no. I wonder if you don't know either. Let's go to slide 50, and we can do it together. All right, so on slide 50 is the residential noise complaint data, so let's download that. So we're asking, does borough have an impact on the type of complaints? Any thoughts on what that answer might be? Yes. Yeah, my feeling would say yeah, and we'll find out. Oh no.
Hello? Hello? Hi Liz, can you share your screen?
Sure.
Thanks.
It's weird, it booted me off, huh? There we go. Is it back?
Yeah. Yeah, it's back. Thanks.
Okay. Okay. Everybody has the data set downloaded? Is it helpful to go back and forth between the slides just so you can keep referring to them? Maybe. Let's do it. Just show you. When you're doing it yourself, I highly recommend going back and forth. If you have two screens, it's even better. Okay. So, first step, insert a pivot table on a new tab. So let's do that. We're starting with the raw data this time. We're not working with what we had been, which was this pivot by complaints by NTA. Start with the raw data. Click anywhere inside the cell, any cell. And we go up to insert. We click on tables and pivot table. Once you get that pop-up box, just click OK. Excuse me. So it's going to create a whole new tab for us. And our next step will be to place the independent variable in the rows and the dependent in the columns. So if our question is, does Burrow have an impact on the descriptor of complaints, the types of complaints? Which ones are independent variable? Yep. So we'll find Burrow. Oh, another, yeah, well, I won't distract us. So find Burrow, and we put that in the rows. And then we'll find, yes, where is descriptor? There it is. Descriptor, and that'll go in column. And then I would take, for this data set, usually when you're running a pivot table, it's kind of like pivot tables plus. If you have a unique key, I would take that when you're figuring out the values. So I'm going to take my unique key and I'll bring that down to values. If you bring descriptor down, that's okay. Basically, the reason I do that is because you want to make sure when you're counting your values that there is a value in every single one of those cells. So if there was a descriptor that was skipped, for instance, it wouldn't count that row as being in existence, basically.
So what does it say count for?
So it's the count of, oops, it should be unique key. And for me, I have the sum and I want it to be the count. So I just need to change it in the value field settings. So just change it from sum to count.
But we have to put in the values, we have to do this descriptor and the Burrow, right? We have to put it in the values.
So in rows, you'll put Burrow.
You don't have to put it in the value, right?
Unique key will go into values. Yeah. Excuse me. So your table will look like this when you're done.
So it's funny because my pivot table automatically puts, you know, the independent and dependent into the value.
Interesting. Even though you don't put it in there. Can you take it back out? I would take your unique key first and put it in values and then see if you can remove the other two. For everyone else, check to make sure that the data is the same for you and that your grand total is 65,530.
I have to change my sum to count.
Yes.
How can I do that? I'll again have to go back to.
So you go to that down in the values quadrant. You click on that.
I was at this stage again. Automatically, so I have to go back to.
If you put unique key down in the values.
Yes.
So you don't have to go back. You just have to change in here in the value field settings. Click on value field settings and just change it to count. How are you doing over there? It's good. Okay. All right. Does everybody have a table that looks like this one? Good. Good. So let's copy it. And I'm including rows 4 through 10 and columns A through F. Hit Control C. And then I'm going to paste starting in row 14 the first time. And don't forget when you paste, you're pasting the values only. So I'm doing that in row 14, and then I'll do it again in row 24, just in case you want to do exactly as I do. So this one looks significantly nicer, but I'm still going to just do a couple aesthetic things. This is not mandatory. This is just because it helps me. And then also don't forget to label your tables. So the first one is observed. And the other one is expected. Want to see anything again? Good. Okay. So the next step is just to delete all of the data in your expected table because we need to create our own. After that, who remembers what the next step is?
Do the sum.
Great. So let's do sum. And you'll want to do sum for columns and rows. Okay, ready for the next step? So for the Bronx banging and pounding, I'm going to type in equals. I'm going to, I mean, I could do it in a different order too. So if it's Bronx banging and pounding, I can go up to the observed table and find the Bronx subtotal first. I'm going to multiply that by the banging and pounding subtotal. And I'll divide that by the total number of complaints. And you can keep going from there. So I'll do it up here. There's also ways, if you would like to, like if you're a little bit more comfortable with Excel, to drag and adapt these formulas, feel free. It's a little more complicated, but it does save some time.
Yeah.
For the correlation formula, is that just for numerical data?
For the independent variable, you can use categorical or numerical. I think for the, let me go back to the grid. No, I don't know that off the top of my head. Yeah, you can do continuous numerical or categorical, and it has to be numerical for the dependent. All right, how are we doing with the grid? Still working? Okay, I'll give you another minute. Again, the big test is to make sure that grand total is the same between the two tables. If you've got that done and you want to move on to the next step, you can just do the chi-square test. So remember, it's the chi-square dot test. And then don't forget, when you're highlighting your actual range and the expected, only the raw data, not the subtotals. So whether or not you're finished, you can keep working on it. If you think you get the gist, then that's good. Yeah, Frida.
What is this? I mean, I understand it means that there is a significant relationship between the borrow and the type of thing. What does that lead you to then? What's the next step from here?
Yeah, it's a good question. So Frida took the next step, which is looking at the p-value. We can see that that's less than our alpha value of 0.05, right? And just be careful. It could look like it's more, but it's got the scientific notation at the end. It's e to the negative 78. So that's a very, 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 very small number.
What's missing is the E.
It's exponentially.
Oh, exponential.
Yeah, so it's 10 to the negative 78, which basically says
Can
you're.
you write the normal way? This is the Excel.
Oh, yes, but it needs to be huge. The column needs to be much bigger. I don't think, if it doesn't have space, I don't think there's a way of writing that differently.
No, maybe you understand. Maybe I didn't understand.
The reason it does that shortened version is because there's not enough space. We would need 77 zeros after the decimal point before we could start the actual number, the 1033. Does that make sense? So this column is too small to fit the full number the normal way. So that's why it abbreviates it.
The zeros go before the 1.
Yeah.
77 zeros.
Yeah.
Can I bring you the paper you written? I didn't understand.
Yeah. Maybe, can we do that at the end of class? Does that work? Or next break?
Okay,
I can write it down. Just
I don't know what it is.
Yeah.
You are right.
But I can. Remind me. I can write what that means.
Okay, maybe we understand what's happening.
Is it better to have it now, you're saying?
No.
Okay.
I want to know only
why. Yeah.
Normal.
Yeah. Yeah. Oh yeah, I could write that out for you. Basically, I mean, that would be a pain in the butt to write. Let's just say it was e to the -7. That's probably easier. Let's just say it was e to the -7. What we would do is take this decimal point and move it 7 times to the left. So we go 1, 2, 3, 4, 5, 6, 7, and we'd have 0.000006 times 1,03321.
Is 7B over there or 7A?
Let's say it was just 7.
Huh?
It's 7/8, but I was giving you an example as if it was 7 because I don't want to write out set -78. That's too big. Well, we could talk about that later.
Yeah, you have different French and English. That's why I'm worried about
no, I totally understand. We can talk about that later. So then the question was, okay, well, we understand what that means, which is there's a significant difference between these two tables. So yes, Burrow does have an impact, or there is a relationship between Burrow and the types of descriptors. And so then the question is, okay, well, so what? And that just requires comparing the table and looking at what is expected versus what is actual, and looking where there's a significant difference or like a larger difference. So for instance, where can we see a large difference taking place?
So there's a significant relationship, is there?
Yes, there is. Here, for instance, I'm looking at loud talking in the Bronx, and it's significantly less than we would expect. So that's a thing to note. We're looking for any difference that's larger than maybe 10. Another place, I don't know, anything that really jumps out at you. Another thing that's worth saying, so if that's one way of doing it, and that's if there's anything that jumps out at you as you compare the two, you can speak to that. There's also something called post hoc testing. And what you do with post hoc testing is, let's say, okay, there's a significant difference, and I understand that the Bronx is pretty different than what would be expected. I want to dig deeper into the Bronx. You can do a post hoc test and do a different test. So it might be a chi-square, or you might design it differently and just dig into that specific information. But that I would say move on to stats class for. It's a little more complicated, the way that it's set up. I have some slides on it, but I lost my last class doing it. I was like, you know what, it's not worth it for you guys. But there are slides too that kind of give you an intro to post hoc testing, and I think you can see them. I know they're hidden from the presentation, but can you all see slide? Oops. Yes. Yeah. And that's exactly why, like, your question is dead on with, okay, well, so what? And then so the rest of these slides talks you through what post hoc, just a really basic idea of post hoc testing. And it's not enough to be able to run one, but to give you an idea of what it might look like. Okay. I have built in here for you to practice on your own, but I'm also looking at the time. I'm aware that we have an hour left, and I do want to do that other test with you. I want to look at ANOVA with you. Can we keep going? Okay. All right, let's do that then. All right, so chi-square tests are cool, but how do I determine if categorical independent variables have an effect on continuous dependent variables. So going back to that grid of ours, if we want to build a causal relationship for categorical independent and continuous dependent. So an example of that, does Burrow affect the time to close a complaint? And we do that with an ANOVA test.
Is this on the slide, this entire?
Yes. Yep. So you can see when it comes to categorical, it can have more than one level or more than two levels, which is good. It becomes difficult and you can only have two. And then we're talking about continuous. So any of the continuous variables. With our data set, let's go back to our complaints. And the question was, does Burrow affect the time to close? So we don't have time to close in our data set right now, but we can calculate it very quickly. So what we're going to do is add in a new column. So come on back to your data, the raw data, and highlight column D. We're just going to insert a new column and then do the math to calculate time to close. So I'm a shortcut keys person. I'm going to type, hold down Control Shift and then hit the plus button. Another way you can do that is just right click on column D and select Insert, whichever is your preference. We're going to call this column time to close. And if I were to do the math to calculate this, what cells do I want to use? Like, what's the formula I need to write? Equals. This is just how long does it take them to respond to a noise complaint and resolve a noise complaint.
Hour of complaint plus 5.
What's the 5? Like, what are you thinking with that? Oh yeah. We want to ultimately find out how many hours. To do that, we want to look at, we have the information.
C2 minus B2.
Exactly. We have the closed date and time, and we have the open date and time. So if we subtract the two, we'll figure out whatever that is, whether it's 5 or what. So we'll do equals C2 minus B2. I got a funky new date. What does that mean? Why did that happen? Yeah, exactly. It took the formatting from the column before it. So we just need to change the formatting. So highlight column D, and we'll come up. Yeah, exactly. We'll change it to a number. Now, if you highlight the whole column, just to make your life easier, come up here.
It says hours to close.
Oh, I did do it. Oh, you guys, that's such a gift to you. I didn't think I did it for you, but I did. You're welcome. Pretend like we didn't do any of that. Just erase it all from your head. It's not normally in the data set. I added it. All right, cool. So let's do it. So step 1 is, oh, sorry, we're doing ANOVA. I forgot. I was about to do the chi-square with you. Let's go over the steps first, and then we'll do it. So when we do the ANOVA, there are 3 different types within Excel. There's the one-way, one-factor. There's a two-way, and that's with replication, and then a two-way without replication. We're not going to get into the two-way and how to do them, but in just a moment, I'll share with you what that even means, just so that you have an understanding. So when it comes to ANOVA, it identifies if multiple levels of a categorical variable have an effect on a continuous variable. So again, like Burrow on time to close. This is done by comparing their means. So ANOVA comes from analysis of variance. It's the abbreviation. And as evaluators, it's the same. It is valuable both before and like a more formative method before you do an evaluation or once you have done an intervention and you want to evaluate it. So when you are calculating an ANOVA test, a couple of things that you need raw data that's categorical, you need raw data that is continuous. And important to note is that continuous, not discrete. Like again, we don't want to look at numbers. We want to be able to do an average and have smaller portions of a number that are valuable. It wouldn't just be an individual account, for instance. We need a null hypothesis, just like we've done. We assume that 0, there's no difference between the two. We need the desired alpha value. We'll use 0.05 as we've been doing. So when it comes to borough and the years living in the city, oh yeah, I guess we could start with our own data. I kind of just want to jump ahead. Let's do it with, we'll do it with the data that we just opened up, the noise complaint data. So when we do this, step 1 is to just prepare the data, create the time to close. I did that for you. So step 2 is to create the pivot table. This time what we do is we will place the independent variable into the columns quadrant. And the reason that we do that is just so that we can paste it into a new row. The next step is that in the raw data, what we're going to do is filter for the first independent variables. So for us, it's the Bronx. So we're going to filter for the Bronx. We're going to highlight all of the values in the hours to close section. We're just going to copy and paste it into our new tab. And we'll repeat that for each of the different stages. So basically what we're looking for, do I have a picture of it? I don't. What we're looking for at the end is a new format for the raw data where we have in each column the hours to close for each of the boroughs. So we're going to have Bronx, all of the hours to close, Brooklyn, and so on. Once we have that, we can run the analysis. So then we'll go to Anova single factor, which is the one we're learning today. The input information is very similar to what we've worked with already. So we have the input range, and that'll be our new table that we created. We'll say it's grouped by columns because that's how we're grouping it. We'll check off of whether we have labels in the first row or not. The alpha value will be filled in, so we'll keep it just as it is, and then we'll choose where we want the output to go. When we're reading the results, this is what the results will look like. Down here, this is the summary, so this is what we would compare when we're drawing conclusions. But down here, the first thing that we want to look at is just the p-value to see if it's below our alpha value. And then we draw our conclusions. A little bit more straightforward, I'd say, than the chi-square. So let's do it. So we're in the raw data for residential noise complaints. Step 1 was to create a pivot table. So let's do that. You'll come up to the Insert tab. We'll go to Pivot Table, and we'll select OK. So the next step is to take the independent variable and place it in the columns quadrant. So our independent variable, if we're asking, does borough have an impact on time to close? Which one's the independent variable? Yep, borough. So let's scroll down, find borough, and we'll place that in the columns. And then I'm just gonna copy it, and I'm gonna put it on a whole new tab. So I'm just gonna copy the names of the column headers. I'm gonna leave grand total off, I don't need that. I'm gonna create a whole new tab, and I'm gonna paste it again, values only. So now I need to fill in the time to close. the time to close for the Bronx we'll start with. So I need to go to my raw data. You know what, I'm gonna label this as my ANOVA table, just so I don't get confused between my sheets. Okay, so in my raw data, I'm going to insert a filter so that I can filter just the Bronx and look at just the time to close for the Bronx. The way I'll do that is by highlighting row 1 with all of my column headers. I'll come up to, in the home ribbon, I'll come over here to the sort and filter button. And then you'll see that last option that's you're able to click on is filter. And I'll just click on filter. So then the next step is to scroll over to borough. There she is. So it's column AB. And just filter. So you click that drop down menu. I'm going to uncheck select all. So that'll deselect all of them. And I'm only going to put a check mark next to Bronx. And then I'll hit OK. So now we can see the filter is on, and how I know is because these numbers aren't sequential anymore and they're in blue. So if I were to scroll through, it would be all just the Bronx. So now I want to go back to the time to close column. Was it D? Hours to close. It's D. So I'm going to click in the very first cell under hours to close. So it looks like it's D15. And then to highlight all of that data really quickly, I'm going to hit Control and Shift. So hold down Control and Shift. And then hit the down arrow. So just a quick way of jumping right down to the bottom and highlighting everything along the way. So then I'll hit Control C to copy it, or you can right click and hit copy. And then I'm going to go back to my ANOVA table tab, and I'm just going to paste everything. So those are all the time to close for the Bronx. And I'll repeat it for the rest of the boroughs. So next is Brooklyn. So I'll come back to my raw data. I'll go back to column AB. In the drop-down menu, I'm going to uncheck the Bronx and just check Brooklyn now. Once I do that, I'll hit OK. Come back to column D. This time I'm going to be clicking in again, the first cell underneath hours to close. This time it's D3. And I can again hit Control Shift down. And that will highlight all of my data that's showing. I'll hit Control C or right click and copy. I'll go back to my ANOVA table. I'll click on that first cell underneath Brooklyn, and I'll paste my values. And you can keep going. Does anybody want me to talk you through Manhattan and on, or are you good? You're good. Okay. Yeah. Okay. So go ahead, you do it, and I'll do it. And then we'll move on to the next step. Does anybody want another minute, or are we ready? Once you've done this, the actual test is pretty easy. So we find the test in the data analysis toolpack, which is up in the data tab, the data ribbon, all the way. Oh, I don't have it enabled. Okay, now all the way at the end is that data analysis button. So I'll click that. And we're running Anova single factor. It's the very first test. And I'll hit OK. My input range, again, you can include the labels or not, I will. So I'm just gonna highlight, actually, I'm gonna click in Bronx and I'm gonna test something out. I'm gonna click in Bronx because there's a lot of data and I don't wanna scroll all the way down and scroll all the way over. So I'm gonna try the same Control-Shift method. I'm gonna go over first though. So I'm gonna click in Bronx, I'm gonna hit Control-Shift and then right arrow. Good, it works. And then I'm gonna hit down. And that should include all of my data. No, it doesn't. I'm gonna hit down again. That should have included all my data. So basically just check. Now you can scroll down. Yes, it included everything. So I've got my input range. They're grouped into columns. That's correct. I have labels in the first rows. I included my labels when I was highlighting, so I'll check that box off. The alpha value I'm going to keep. And then for my output range, I just made a little spot up here. So I'm going to make my output range G3 for me. You can put it wherever you'd like. Once you've got all that filled in, you can hit OK. And you get a nice set of tables. My eyes immediately find the p-value. That's the most important thing when you're first deciding what the conclusion is. I have a p-value of 0. So is there a significant impact when it comes to Burrow and time to close? Does Burrow have an impact on the time to close?
So was the left is greater than alpha?
Then yes.
Then what?
It's the same as usual. So if it's greater, then there's no difference. It's not statistically significant. But if it's less than, then there is a statistically significant impact.
0 is greater than 0.05.
0 is,
No, it's less than.
I know, isn't it crazy? It just like messes with you. It's less than. It's less than. So there is a significant impact. Burrow does impact time to close. And my gut would have said that yes, that makes sense.
So I don't understand that question. Burrow has impact on time. So what does it mean?
So what's the point, right? Like, what does that mean? That's where we might start looking at, okay, well, that's good to know. Burrow impacts time to close. This is, again, where post-hoc testing would come into play. So I can't say, okay, well, which burrow? Because that would be my next question. Are there any burrows in particular? And then maybe also, I guess we could look at the average time to close.
Yeah.
And we know that that's significant, right? So the Bronx is significantly longer than any other borough in its time to close. So being in the Bronx means that it will take longer for your complaints to be resolved. And we can make that. That is 100% an accurate statement.
So that time is like 4 hours, 4 days, or
Hours.
hours?
Yeah. It's not terribly longer.
For us, it's still within the day.
Yeah. Yeah. So is it worth reporting? I don't know. Is it significant? Yes. There's a difference.
If you're on the trading for every second counts, so
Yeah.
that's the thing.
Yeah. So you see that, does that help with like the, so what, like what's the next piece? I might have a question from there. Okay, well, the Bronx takes the longest. Are there any descriptors that are longer than any others? We might do a follow-up test on that, and that's how you would dig deeper. So then we would say, okay, we'd filter for just the Bronx, and I might run a test now of the descriptors. Is there descriptors and an impact on time to close? So you just dig deeper, and we keep using the same tests. Any questions about that? If I wanted to dig deeper, here's a challenge question. I'm going to pull up my table. If I wanted to dig deeper and I said, okay, well, I want to know more about the Bronx and the time to close, which descriptors, or are there descriptors that have a more significant impact on time to close than others? Which test would I run? First of all, which one's the independent variable? If we're looking at descriptors and time to close. Not the borough anymore. So I'm going to filter out any other borough. So we'll just look at the Bronx. But we're looking at descriptors and time to close. Does descriptor have an impact on time to close? Descriptor is independent. And is descriptor categorical or continuous? Categorical. So we would be looking at really any of these we could use. So then the next question is, based on the dependent variable, time to close, is that continuous or categorical? Continuous. So that would eliminate chi-square for us. And we would want to use one of these other. Now, actually, let's go back for a second. Do we have 2 levels or more than 2 levels in our descriptor?
2 levels.
More than 2 levels. Yeah. So that would actually eliminate correlation in t-test. Being continuous would eliminate chi-square. So we would be running another ANOVA.
Why do we have more than 2 levels? Because we've got more than one file.
We're only looking at Bronx, but we're looking at the descriptor now. And remember, there were at least 4 descriptors.
Loud noise, television.
Exactly. Banging, pounding. Mm-hmm. So do you see how I would use this table to figure out what tests we're running? And we'd go back to ANOVA.
4 descriptors, continuous. So it can be correlation, it can be ANOVA, and it could be the 2-way ANOVA.
Correlation we couldn't because it's only 2 levels.
Yeah. So it could, so it's
One of these 2. So when it comes to the 2-way, because I said I would let you know what that is, the reason it's more powerful is right here. You can use more than one category. So we just broke it up into 2 different ANOVA tests, but I could say, okay, if I wanted to run the 2-way factorial ANOVA, I could say, does borough and descriptor have an impact on time to close? I could run it all at the same time, and I can get a p-value for each of those, and it'll tell me together, does it have an impact? And then separately, do they have an impact as well? So it just saves you some time.
Liz,
Yes.
I just want to make sure. So here we're still looking at correlation instead of causation, right?
No, we're looking at causation. What impacts the other?
Okay, so we can conclude that there's a causation.
Yes.
Oh, okay.
But again, it's go back to, remember when we were talking about you need the design plus the test? So you can't just have a test and be able to say that there's a cause and effect relationship. You need to have a study design that eliminates any other confounding variables.
Okay.
And so it goes back to that example of, what was it, margarine consumption in Vermont? Oh no, it was divorce rates, right? Margarine consumption and how the 2 were related to each other. When margarine consumption went up, divorce rates went up. But it's only, we couldn't say that one causes the other. That sounds ridiculous. And it's because there's a confounding variable. There's something else that's impacting those two things at the same time. If you have a well-designed evaluation, you're controlling for those other things. And so you can make that conclusion about the cause and effect relationship. Does that make sense?
Okay, yeah, it does.
Okay. Any other questions?
Yeah. So in the first test, one way ANOVA, we got those average time of the 5 boroughs, which bronze was the highest, like 4 hours. Now, if you want to dig down deeper, out of the 4 descriptors, which is using more time or which is less, then you would do this, you can do this two-way factorable.
You could, yep.
Good. So the question you flip is which descriptor has the impact on the closing time?
If you were to do the two-way, I would say do both of them at the same time. So I would say instead of do borough and month of the year affect the time to close a complaint, I would say does borough and descriptor affect the time to close a complaint. So you would do it all together.
Be like which descriptor or which is taking more time to close.
Yes. Yep. Alternatively, you could do it by hand. We just ran the first part. We know that Bronx is the longest. So what I could do if I didn't know how to run the two-way is I'd go back to this raw data. I would filter just the Bronx. I would just pull out only Bronx data, and then I'd look at descriptors. So for my ANOVA table, across the top, I'd have the different descriptors and then the time to close for each of them. Make sense?
You design it to answer your question.
Yes. Exactly. Any other questions? So this slide is just reviewing what we talked about, what the two-way does. And it gives us 2 or more categorical variables that we can compare. I wanted to also add in regressions because they're really popular. Regressions can be used for multiple things. If we're looking at a cause and effect relationship, the factors that you need to consider is that for your independent variable, it needs to be continuous. And your dependent variable can be either continuous or categorical. So that kind of closes the loop. I think looking at this table, just about any data combination that you have has a test listed up here. So when it comes to the test, you know, people wonder, okay, well, is there one test that's better than the other? And it's not necessarily that. It's more so you choose your test based on the type of data that you have. What I will say though, if we want to add a layer of complexity, is that I find that with chi-square and correlation, that they speak more to the relationship and less towards the cause effect. You really, really need that well-designed study to be able to speak to cause effect. Whereas the other ones, it's very clear cause effect. Again, you need that well-designed study, but it's a little bit more clear. Kind of like Simeo, you were asking with the chi-square, does it matter what's the row versus column? It really doesn't, because again, it's speaking to that relationship more.
Okay, yeah, got it.
Yeah. Any questions for me? I think the biggest thing to take away from here is, one, how do you run these tests? Like step by step, how would you run them if you wanted to? I would encourage you, if this is something that you're really into, I would encourage you to take a stats class, and I would for sure encourage you to find a different method beyond Excel to do these types of analyses. For you, really, what I would hope for you to do is to understand what we're talking about, these bigger concepts, the ability to interpret results, to know what ANOVA is, how is it valuable to you? And if somebody has results, to be able to understand what they're talking about. This is the job of statisticians. You hire and or work with statisticians. You may be one, and that's amazing. And this is the training wheels. It goes so much deeper. Okay, so in terms of homework, homework, we have, I can show you really quickly what the homework looks like. It's just one page, no readings at the end. You made it, congrats. The question that I'll have you answer and play around with is, what can be learned from other indicators of the quality of infrastructure and services within the city? So you'll be using the sanitation complaints data, and you'll be running a chi-square and an ANOVA off of it. And then again, this is what is valuable to me, is making sure that you can draw conclusions. So being able to run the test is great, but more important is, do you know what it means? And that's where the real value is. So that's your homework. What I would ask is that for this assignment, you get this in, oh yeah, here it is. You get this assignment in by Monday evening. So that's March 2nd. Like I said, I'll grade it by Wednesday evening. And then I'll give you until the following Monday, March 9th, to submit any corrections that you want before I do final grades. If you need more time than that on anything, just speak to me and we'll figure it out. I'm always here if you have any questions, just because I'm not physically here. And if we want to like hop on a Zoom because you want to show something to me, or I want to show something to you, we can do that too. And then also make sure you complete any readings for your next class before that starts.
Great. This semester will be after we complete the quantitative. So those months will add them together.
That's right. Yep, they'll be averaged together, which is good news for people who don't love stats. You get averaged in with the qualitative.
We don't even know what that's going to do.
When does the other class start?
It sounds like it was 2 weeks. So you have a week off.
Yeah.
Oh, good to know.
So it would be the 10th, right? Yeah, don't come here.
We've got to do the homework.
So, sorry, so we won't get the final grade until the next 6.
That's right. Yep. It'll just be one lump sum. If you want me to calculate what yours would be for this, just so you know, I can do that too. Yeah. Just shoot me an email at the end and let me know. I can do that. That's not a problem. Okay. So just to summarize everything that we've talked about. So the goals for monitoring and evaluation is to gather useful data in a credible fashion. And we talked about how to go about gathering that data. To make sure that you analyze it accurately. And so we talked about some of the ways to do that. And then to learn from and take action on its results. One thing I might add to that list is to design a study that helps you to analyze accurately and learn from the information. So when it comes to quantitative design, some things to consider. How can I create the strongest evaluation possible? It takes into account both reliability and validity. Participatory is an important asset of that, so making sure that you're including your stakeholders at every step along the way. If you're conducting an outcome or an impact evaluation, things to consider. What does the design need in order to make the case for a causal relationship? So what confounding variables do I need to take into account and either control for or just at least acknowledge that they're there? So an experimental design is the most beloved method, but quasi is okay. And quite frankly, in social services and any like social sector, quasi is just more practical. And we talked about the reasons why for that. And then more than anything, make sure you use randomized sampling.
That's the most important when you're actually doing that, choosing your population. When it comes to quant analysis, some things to look at: what kind of data is it, continuous or categorical? So making sure you know the difference between those two. What are its descriptive characteristics? Just to share kind of like your summary of what the data set looks like. Central tendency, variation, relationships between the data, distributions. Those are all important things to be able to share. And then the question is, what inferences can be made? Like, how can we summarize that population, especially if you did your random sampling, to the general population? And so what measurable differences are there? Are there correlations between any of the variables? So in these 6 sessions, we established the whys and the hows of quantitative analysis. And in your next 6 classes, you're going to talk about qualitative. There's definitely some overlap. And in particular, what you're talking about, what they are, when to use them, how to use them responsibly. And I'll go back to the idea of how they're really married, and the strongest evaluation incorporates both of them. So to really understand both of those aspects well is important. And that's it. We made it. There's So this is my personal email. Like, that's my business. That one's not going away anywhere. I'm not planning on leaving NYU anytime soon, but have that just in case it bounces back for whatever reason. Thank you guys. You all have been so wonderful. You're so sad. Thank you. And please take some sweets before you leave, because I don't want them. I'll take 8 cookies. And yeah, let me know if you have any questions or if you need anything. And like, I'm here, so if you have a question in like a year, let me know. I'm still here. I won't ignore you, I promise.
Thank you. I'm just unable to answer all my questions because I have little questions. Thank you very, very much, madam.
My pleasure.
Thanks, Liz. Have a good night.
Have a good night. Boubacar, do you want me to write out?
Oh, for those ones is good.
Hold on one second. Let me stop this recording.